There you go. Cool. So I'm recording right now. Let me know if you need anything. All right, let's start. Actually, one second. Let me pause this. I think I got a text. Zoom recording. Okay, that's okay. That's fine. They seem to be. All right. Anyway, so OrCad, and welcome to the OrCad Advanced Workshops. I'm glad you guys are all here. You guys are probably the best students in the ETD class. Let me make it presentation mode. All right, and I'm Gabriel. A little bit myself is I was previously Rakesh's student as well. I think a couple semesters ago, I also took ETD. I have a 4.0 GPA. I also got a pretty good mark in this class. So if you have any questions, please don't feel free to stop me at any time. The first thing I want to talk about is a little overview of this whole presentation. So we're going to talk about different concepts. So basically CMOS and TTL. I'm gonna quiz you if anyone wants to participate. Do you know what CMOS and TTL stand for? I know you know their acronyms, but do you know what they stand for? If you don't know, that's okay. I'll leave that in the back burner for now. And after we talk a little bit about that logic, we'll be talking about BJT transistors and Darlington transistors. You'll realize that both of them are pretty similar in the calculations and their behaviors. However, there is a slight difference that you will see. It's mostly the diode difference. So there's one has one diode and one has two diodes. So you'll see that later. And I also want to teach you guys how to add libraries onto OrCad. I believe this is a very important skill that you might not have been taught before previously. And eventually you will need to add that for the new MOSFET transistors, which is not currently in the default libraries of OrCad. So the IRF 840 and the IRF 9510. And it's good that I restarted my computer so that I installed a fresh OrCad system on mine. So you'll see firsthand what I'm talking about later. And then if we have time, I want to talk a little bit about level shifting, but you don't have to worry about that too much right now because that's more advanced concept. I'm not expecting you guys to know. I just want to teach you guys how to use OrCad and basically the different behaviors and what to do with them right now. So don't worry about the level shifting too much. They will talk about that more maybe some other time, or you can learn that in ETD class. Okay, so a little bit about CMOS logic. So what does CMOS stand for? So it stands for complementary metal oxide semiconductor. So if anyone owns a desktop computer, a lot of people tell you to reset the CMOS sometimes when something messes up, you get a blue screen of death or something. This is mostly the battery that's in your system. It's mostly there to keep your clock, your time, your system time. Sometimes people take it out and put it back in to reset their system. And you will see that's one of the fixes that people use. That's totally unrelated to what this is for. But if you've seen those batteries, you know that they are 3.3 volt batteries, lithium batteries. They're like this thin, right? And that's kind of what I want you guys to keep in mind. When we talk about CMOS logic, when we talk about logic high and logic low, it's usually when you put the battery in 3.3 volt, or when you take the battery out, which is 0 volt. Simple enough, right? And the other one that we talked about is TTL. So TTL stands for transistor logic. So this basically this is just different concepts for logic low and logic high. So from logic low, there's more of a range. So it's from 0 volts to about 0.8, 0.7-ish. And the logic high is from like 2 volts to 4.95, maybe like 5 volts as well. So in our case, it's probably safer to make it like 5 volts. So you'll see where these concepts come into play when we actually build the circuits. And the first circuit we're going to build is the 2N3904. It's an NPN transistor. And don't worry about all these calculations right now. I'll talk more about that later. Let's just try to build the circuit together first. Let me stop my share. Okay, cannot minimize. Okay. 1 second. Let me just get my OrCad out. Sure. Sorry, it's a little laggy on my end. Let me just get it out. Screen 1. Okay. All right, so I just started OrCad. I believe most of you hopefully have it installed. I think Rakesh has probably put it in your course documents or like somewhere in Blackboard, this OrCad thing. So you can also use MyApps for it. I personally don't really like using MyApps because of the network issues that can come into play when you're trying to do like a lab test or something like that. So it's not really my thing. I like installing it on my desktop. And you also have some in school as well when you're doing the lab, but it's better to do it at home, right? So the good thing about OrCad is you can test your systems without actually breaking anything. So that's good. I break a lot of components, I know. So let me refresh you on how to use OrCad, right? Just a little refresher. So when you want to make a new project or new design, you click on new project. And you make sure that you pick the analog and mix AD. So this is so you can add power supplies and things like that. Because if you use any of the other ones, it's kind of for something that's a little bit different. So for our purposes, we used this A analog or mix AD. So now let's just name it maybe circuit 1. I'll give it like a simple name for us. Actually, I'll just name it today's date, June 7th, 2021. All right. So let's see. And then I usually just create a blank project. I don't like the existing project. Yeah, you just create a blank one. It's better. Okay, cool. And then when you do the start page, you'll see this. So you can still see my screen, right? I hope. So how do you add components? One sec, let me move me aside here. All right, how do you add
Yes,
components?
everything okay.
Oh, thank you. All right, so when you want to add a component, you click on this little thing over here, place part. And let me just delete all this libraries here first. Okay, so now it's pretty blank. There's nothing here. So what do you like? How do you add parts? So first thing you need to do is you click on this add library thing, and it will give you, let's see. Oh, I have to go to my desktop. So usually when you install OrCad, I install it on my C drive, but you can install it anywhere else. That's fine too. And I believe it's in tools. Is it in the tools? Lib. Hmm. 1 second. Let me just try to check something real quick. OrCad. All right, tools. Yeah, tools. And PSpice and library. Here, distribution, library, tools. I think it's in capture actually. PSpice, tools, capture, and library. Here. And I think we click on PSpice. Yeah, here. Okay, so you see a bunch of OLB files. So this is how you add things. So if I wanted to add resistors, I usually use the eval A and as well as the source. And to be honest, if you just want to add it all, you can just kind of like add it all at the same time, which is what I usually do. And then you can pick and choose from here. So see, now you see all these components here, right? And let's say we want to create the MPN transistor as a switch logic, which is this picture right here, which I will recreate for you guys, so don't worry too much about that. So the first thing we need to do is we need to add a power, like we need to add some resistors. Let's add some resistors first. So when you click on resistors, it's usually in the eval A, and then you'll see big letters resistor. And then you can put your resistors in. Oh, that's not resistor. And to get out of it, you just kind of click escape. All right, so here, and then I put like, I think we need 2 resistors for this. And to rotate it, you click, I think control, actually you can rotate it like this. Yeah, that's what I do to rotate it. I think it's also Shift R or something like that, the shortcut. I can't remember it for the life of me right now. Yeah, and then you need a power supply. So power supply is usually in this thing called source. And we need a VDC. So that's kind of like the battery I was talking about before, the CMOS battery. Where is VDC? There it is. And you double click it to select it. Here. Okay. So 2 power supplies. And now we also need a transistor. So transistor, I kind of forgot where it's from. So this is what I do when I try to find components. I kind of highlight all the libraries. And then I look up here and I type in, this is to be 2N309. And that's how you can also find components. See, and C will tell you which library it's from as well. So this is from the eval library. So maybe you'll try to remember for next time. Usually I forget as well. So this is what I do. Yeah, and you click it here and then escape when you don't want to add any more components. Yeah, and then we also need, sorry, hello? Do you have a question? No, not yet. Okay, cool, cool. Yeah, and then now we also need to add a couple grounds so that we can complete the circuit. Do you have a question? Someone has a question or just have your mic on? That's okay. Yeah, so usually you click on this ground symbol over here on the side, and then you kind of click, yeah, you just find the 0 and press OK, and then the default should be fine. So the ground is here, and I'll put a couple of grounds. So we need about like 3. You can actually connect the grounds to all be the same. It's neither if you put separate grounds, which is what I do. But technically you can connect them all together as well, which you can also do it that way. I just prefer it this way. And now we need to make a wire connection for all of them. Let me actually zoom in. Maybe they'll be clearer. Yeah. Maybe it'd be a little bit clearer for you guys if I zoom in a little. Let me put it closer a little bit. Yeah. Okay. So, and then you press on your keyboard W, you can get the wire, or you can also click this thing right over here, which is underneath the components to get the wire as well. Whichever you prefer, as long as you connect them, there's no wrong answer. And then you put it here, here, and this one goes into the power supply, and then goes to ground. Okay. So any questions so far? Is it super clear right now? You guys are experts, so you have no questions. That's cool. Yeah. Well, so this is more or less how to kind of recreate the circuit that you will see in I think you already maybe seen this in ETD. This is your first couple of weeks. I think you might have already seen a resistor as a switch circuit. And you can also change you can change the values by double clicking them. And then maybe you put 3.3 here instead of 0. And then we can make this 1K. This is usually, since it's the base resistor, this one's usually bigger than the emitter resistor, right? I mean the collector, there is collector resistor, which is on the other side. So I put 10K here, and then we can leave this as 1K. I think that's the calculations I did on the PowerPoint. We will also post the PowerPoint, so don't worry. And we will post a recording of the video so you guys can review it. I'll bother my IEEE executive team to post it up on the YouTube channel for you guys. Yeah. So usually the V2, we keep it at like a consistent power for these kind of methods, this kind of circuits. Is mostly because do you guys know why we have it? We have 2 separate power supplies and like looks like 2 separate circuits. Do you guys know? No? No response. That's okay. Yeah. So usually when you want to make microcontroller circuits, you want to separate the microcontroller from the larger load circuit, mostly because the microcontroller might not be able to handle the larger current draw, and it might break the circuit. It might break the microcontroller because they're very finicky kind of components, and they cost a lot of money usually. I think a Raspberry Pi costs about $100. Maybe costs like more than 100 as well. Like, when you work in a workplace, they probably have like thousands of dollars worth of microchips as well. So you don't really want to break the microchip, which is the brain of the circuit. So which is why you separate it with kind of like a transistor or different methods as well. Like if you heard of motor drivers, they're basically just transistors in like a more packaged form. Yeah, so V2, V1. So now we want to see the values. So before we see the values, I want to go over a little bit about the calculations. I don't know if you've been through the calculations before, but let's say we're using CMOS logic. So remember when we just talked about CMOS, we're talking about 3.3 and 0, like the battery. So let's say we want to know what saturates and cut off like that cuts off the circuit. So what does saturation and cutoff mean? Does anyone know what they mean yet? No? Or still kind of confusing concept? If you guys want me to elaborate, totally let me know. But in briefly, it means that cutoff basically means the circuit on the load side is not working, and saturation basically means that it is working. And the short story, I guess. Okay, so first let's walk you through this calculation. So let's find out when VBB is 3.3. So VBB is V1 in this case, which is the base voltage. We call it VBB. And the VBE is from the base to the emitter. So emitter is where the kind of the source goes. And then R2 is kind of the load resistor. You guys kind of understand so far, I hope. Yeah. And how do you find IB? So let's look at the formula that you should probably have. The IB is equals to VBB minus VBE and divided by RB, which is the resistor value R1. So 3.3 minus 0.7. So why do we minus 0.7? Because it goes through this diode over here, and we're thinking that is a silicon. I believe that is the material. It's going to be 0.7. So I think germanium is 0.3 or 0.4. So in this case is silicon, so it's 0.7. And it goes, so since the ground are all connected, this will be connected as a circuit. So we're kind of looking at this as a separate piece. So this is how we're trying to figure out what the current of IB is, what the current running through the circuit is, the separate circuit is. So the IB will be around 260 microamps, which is kind of small, but let's see if it's enough. So when you go to beta, so beta is kind of like what the load side kind of exponential of the transistor. So usually beta is around, I believe, 10 to 30. But for our cases, because of the class, like theoretically, we'll put it to 100. Oh, I apologize. I'm gonna mute you, Van Den. I apologize. Unless you have a question. You have a question, Van Den? No? Okay, I'm gonna mute you. I apologize because it's a little bit, unfortunately disruptive. Yep. Okay. Okay. So yeah. So when you do beta, it's usually 10 to 30, but for our purposes, we make it 100 or 1,000, which you'll see later. So we kind of, so how do you get IC? So IC is the collector side current. So in this case, it's this kind of current. And IC will be beta multiplied by IB, which will be 26 milliamps. And then from there, you want to find out what the VCE is. So what the voltage from the collector to the emitter is. So this will tell us if the circuit is basically working or not working, right? So how do we find that out? So it's VCC, which is this 12 volts minus ICRC, which is minus the voltage of this resistor. And when you do that, you get 26 multiplied by milliamps multiplied by 1,000 ohms, right? 1,000 ohms, which will create to a minus 14 V resistor, which kind of means oversaturation, because it is because it's yeah. Well, actually, I'll explain that later. You guys can think about it. But it's so that basically means because it's impossible to get a minus voltage in this case because it should only go one direction. It is going to be an oversaturation. And then we do the calculations for 0. As you can see here, you just follow the same steps. And you come up with 19 volts, which is also impossible because the highest voltage here is 12. So it'll be a cutoff. And why is that? And we'll go through the logic here. So the saturation logic is when VCE is equals to 0. It is saturated, so it is working. And IC equals to VCC divided by RC. This is the formula you can get for IC. And when IC is 0, it is cut off, so it's not working. And a VCCE equals to VCC, which is in this case, it would be 12 because it's impossible to be 19, so they will be the same. right? So in this case, it will not, yeah. So that's a cutoff. Do you guys kind of get it? No questions so far? Okay. So let's see this in OrCAD and see how that goes. Yeah. So
Question.
you have a question? Cool, cool, cool. Yeah, what's up?
So just I want like the highest value of the IC, it should be like VCC divided by RL. So we could not have the value like above that. So because if we keep increasing the VBB, then at some point the IC will get bigger than when we say IC is equal to VCC divided by RL. So what I mean that the IC cannot go beyond whatever the answer, the result it is from VCC divided by RL, which is that is like hard saturation or full saturation.
Yeah, you're perfectly right. Yeah. So that is, yeah, this is one of the more advanced concepts that you were, maybe I think Prakash might have already zoned it on this. But yeah, so the circuit itself cannot be higher, the IC cannot be higher than the circuit limitations, right? Because our V is only 12 volts. The circuit limitation for IC will be VC divided by R2 in this case, in this what you see on my screen here. You're 100% right. So that is why when I did the calculations, you see that 19 volts is impossible because this is like over the limitation of what 12 divided by 1K is, because 12 divided by 1K is 12 milliamps, right? So it's too much. So this, apologies, not this one over here. So 12 divided by 12 divided by 1K is 12 milliamps, and 26 milliamps is way over that, right? So that's impossible. So that's why it gives me an impossible number, which is this, right? So does that answer kind of like your doubts, or not really?
Thank you.
Yeah, does it make sense? Okay, cool. All right, so now let's see the fun part, right? The fun part is you want to see this working. You want to see the graph. Okay. So let me do this way. So we want to make a simulation. So we click on this thing up here. You see this? You click on this, and let's do the first thing. We'll do the bias point one first. Bias point. And we'll create it here. And let me see if it pops up. Where does it pop up? There you go. Okay, okay. So you guys still see my screen? Do you see simulation settings here? Sometimes you can't really see it. You guys still see it? No? Yeah, maybe. I'll just take that as a yes. So I'm gonna keep explaining. If it doesn't make sense to you, let me know. So there are a couple of things of analysis type that you might have not remembered. So I'll do a little review. So there is the time domain one, which is something you want to see if you're trying to look at something that's going over time. Excuse me. So this is kind of like for capacitance. So when you do have a capacitor, it does charge up the capacitor in the sense over time. So sometimes you want to use this kind of simulation profile. And then there's also DC sweep, which is what we are going to be using because we want to see the differences that changing the VBB will make, right? We want to see what part becomes cutoff and which part becomes saturated. And then there is AC sweep, which is dealing with the same kind of thing as DC sweep, but it's for AC's power sources. That may be something you learn in the ELD class, or what's the other class? HSI, maybe. And then there's bias point, which is what we're going to use this time. Bias point is kind of just to show the different values that it currently has right now. So we're going to, in this case, do 3.31K and all these other values. So I'm going to do, and then we're going to keep the general setting, press OK, right? And then we'll start it. And then in this case, you will see all the numbers, right? And this is kind of good to have because then you can kind of see if your calculations match the circuit, right? So let's say now it's 3.3, so we'll follow this value. And then IC should be around 26 milliamps. So is it 26? No, right? It is 11.87. Like you were saying before, I forgot who was talking. I don't remember, but whoever was talking before, you see now that's only 11.87, which is close to 12 milliamps. So why is it not 12 milliamps? Because that's kind of a theoretical number, and this OrCAD tries to simulate real real circuits. So usually you don't get the perfect number of 12 milliamps. You get maybe something a little bit less, something a little bit more, right? So in this case, it's usually a little bit, yeah. So you'll see in the labs, I hope, as well. So in this case, is yeah, the maximum is 12 milliamps, and so that makes sense here. And then what is VCE? So VCE is the, you can't really see that here, I guess, but like it should be 0, right? It should be 0 volts, right? As you can see. And then you can kind of change the numbers up to see the 0, and it'll be kind of similar to that as well. Do you guys want to see the, if I change it to 0, are you guys fine with this so far? You're good? I'll take that as a yes. Very quiet workshop this time, but it's okay. Oh, someone talked in chat. Yes. Oh, do you want to see it in 0? Okay, I'll show it in 0 then. Yeah. I apologize. I know some people don't have mics. Let me stop this. Okay. So let me change this to 0. And then when you want to do another, so just change the value to 0. And then when you want to do the buy point again, you're just gonna press the play again, and it'll change. And then you'll see here. Okay, and then we'll see the calculations again. Hopefully you guys can see my calculations. I know it might be kind of small font, but yeah. So when I do 0, it'd be the IB, so it's been minus 0 UA. So essentially this means 0, 0, 0 current, right? Essentially, because it's 0 amps, 0 volts, so it'd be 0 current. So this one says 16.29 pico amps, which is kind of similar to 0, right? Because it's more like real time. And so it's basically 0. IC is basically 0. So that's right. IB is right. And then you'll see minus 7 milliamps, which is also 0. Which is also 30.3324 pica amps is also counts as 0. We can also assume that it's 0. Because it's very small. And actually we don't need power. Let me take out power. That might be confusing to you guys. Yeah. And then you see that there's 0 volts down here, but 12 volts up here because it is cutoff. And as you can see it here, it is similar to our impossible cutoff, which is 19. So 12 is the perfect number for this as well. It should be 12. So everything's right. Everything checks out, right? Yeah. So this is what you can do when you're trying to go through the calculations. You need to test your answers. You can kind of see. Yeah. So this is kind of fun, but it's not as fun as what I'm going to show you now, which is the graph, right? How do you do the graph? It's sometimes very confusing, very complicated, but I'll show you. Don't worry. So we're gonna make a new simulation. We'll call this, let's say DC sweep, because that's what we're gonna do. We're gonna do a DC sweep. So we're gonna create this, and then you'll see the settings. So you guys see my simulation settings here. We'll do DC sweep, which is right on this right over here. Yep, and yeah, and then we void source. So you pick the one that you want to change usually. So usually we don't change V2. I'm saying usually a lot. I apologize. So you pick V1, put V1 here. And then what you want the start value to be, let's say 0, because that's what we start with. And we want CMOS logic is up to 3.3, but let's say 5. Let's say we're doing TTL logic just for fun, right? And sorry, I have trouble drawing my ups, but I have problem with voices. Okay. We'll check that out later. I apologize because I would only have an hour. It's already 30 minutes, so I kind of want to go through more. When I have time later, I'll let you know how to do that. And we put a 0.5 and you put it apply. And then you pick the thing. No worries. No worries. Okay. And then you'll see a graph pop up. Might take a couple seconds. Don't worry. The rest of this will go by faster because I already implemented that. Oh, we forgot something. I apologize. Forgot something. So before we play this, we already set the simulation profile. We also want to add the probes. So the probes kind of help us determine, see the probes over here on my little picture, what the IC and all those other things are. So we want to know, let's say we want to know what IB is. So we click the I, which is basically current. IB, we want to know what IC is. IC is up here, the collector. And then we also want to know the voltage, let's say. We want to know the voltage of IB. So we'll put it here, and then we'll put we want to know the voltage of VCE. So VCE is kind of hard because it's only like there's a C here and there's the E here. So we need to use the differential marker. So we put like 1 on the C and we put 1 on the E. So in this case, I put 1 here and I put 1 here. Right? Makes sense so far? Yeah, good. Okay, and then we'll play it, and then we'll show a simulation, which is over here. And you guys can see the graph right now, right? Little messy, right? Little messy. Can you tell what's going on? Not me neither. Right? I can't really tell. So you want to separate the voltage and current into two different things that will make things a little bit clearer, probably, right? Because right now we're not really sure which is current, and it's kind of really confusing.
Gabriel,
Yep.
can I take a second?
Yeah, no worries. Go for it.
So, look at, he's a so passionate, lot of knowledge, and he's sharing step by step. So let's say everybody give a virtual round of applause to Gabriel. Everybody give a virtual round to Gabriel.
Thank you, sir.
Okay. If it would be 1-to-1, we could able to have a, big clapping. So once again, we truly
Thanks.
Appreciate, Gabriel, what you're doing for everyone.
Thank you.
And fantastic, great job. Keep it up.
Thank you, sir.
That's really absolutely awesome.
Thank
I
you.
do have another commitment, so I might need to leave. But
Yeah, no worries, sir.
truly appreciate that what you are doing for everyone. Okay.
Yeah.
Great
Thank you for
job. Keep
popping
it
by,
up.
sir. Thank you.
Okay. All right.
Thank you for helping organize this. Yeah, thank you, sir.
Bye-bye.
Bye, sir. Okay. Yeah. So yeah, I apologize. Hopefully you guys are learning. Yeah. Student VPN. Thank you, Tennis. Thank you for the virtual claps. This is all in the recording, so it's gonna be super awkward when we watch this again, but it's okay. Don't worry. All right. Okay. So a little bit confusing, right? So we want to make a separate plot. Let's do a separate plot right now. So we add a separate plot. We click one here, and then you'll see a separate plot here, but it's empty. We want to put the current over there somehow. So if you guys have ever used Microsoft Word, or you want to copy like a link over to your like bibliography and things like that, right? You can do Control X. Let me do the current up here. So Control X, it gets it out, and then Control V, and you paste it here. So you can do the same thing for the other one, right? And then you can see the graph now. So now it looks a little bit clearer, right? I hope for you guys. Yeah. So as you can see, the graph here for RIR1 and IR2, which is the base, if you don't remember, is the base resistor right over here. It's increasing as the voltage increases. That makes sense, right? And now IR2 is basically the IC, the load resistor, and then we're doing the VCE, which is the other voltage you see here. So you can see that it is 12 volts first, and then there is a switch into around maybe 0 volts, around 1.5 volts, right? So that is because the cutoff is around here. So when you see in the lab, when you do the calculations, I believe it's around like 2 volts or something like that. But it's real. This is like a real-time thing, so it's not really exactly the number, but you see that it's around here. So this is why we use like you think about doing this with different circuits. So when you do like implement this maybe in the real world, or like when you have a job in this kind of field, you'll see that which logic you want to use. When you use CMOS, which is kind of more tight 0 to 3.3, or you want to use TTL because sometimes the cutoff point is like a little bit further than 3.3 volts, right? So sorry, someone has a question or no? Okay. Yeah, and then if you want to see the values, you can click on this thing called cursors. You can toggle the cursors so you can see maybe like if you want to see here, it'll be like, and then it'll tell you on this end over here, 1.5, maybe 1.49 volts here. Yeah. So yeah, if any questions so far, no questions, cool. All right, let's do the other one. So there's the PNP logic, and then the rest is kind of straightforward from there. Yeah. So the thing to know about this compared to the other thing that we're talking about later is that it is current driven. So keep that in mind, current driven. There's another thing that's voltage driven later on that you might know later, that you might learn about later in ETD. Okay. Yeah, so now I want to just open new project. So I'm gonna just say, I don't really, just save it, sure, why not? Okay, so let me open new project. So when you want to open an existing project, you can go to open project, and you can go, mine's in the desktop, OrCad, library, not library files, workshop. And then we do, this is the PNP, which is the 2N3906. And the schematics is already there. So when you open it, it's gonna go look like this, and then you kind of click here, and then you click on the DSN, the schematic is right here. I never name my schematic, you probably should, but I'm I'm a bad example. You guys don't follow my lead on this. All right, so this is a this is the PNP. The PNP kind of follows the same as I said before, saturation. A VCE equals 0, IC equals this, right? You guys kind of get it. Yeah, then yeah, so the calculation is a little bit different. So when you want to find IB, there's a lot more involved. You got to do VEE minus VBB minus VBE divided by RB and stuff like that. So this is very confusing to you because what is VEE, what is VBB and all that stuff, right? So VEE is the emitter side. So you can see that the diode has switched. The diode's on the other side right now. And when you see it here, let me see if I can find Q 2N309, 306, my bad, 306. Is it not popping up? Oh, there we go, here. Use this one. So when you pop it up, it's gonna look like this. And the important thing to know how to change this. Important to know how to change this because you want to make it look like this so it looks neater. You can flip it. So there is this rotate button. There's also mirror horizontally or vertically. So usually I do, I think, not this, not horizontally, vertically. And then you can make it look like the circuit that I have right now, right? So that's a good thing to note, just so you can make it look neater as opposed to kind of drawing lines everywhere. It's very confusing, right? But yeah, so a little more involved because there is more calculations. So you got more involved because now you have the emitter side as well that goes into this. So it goes kind of like this way. This large circuit that if you follow my cursor is kind of like what we have to calculate. So it's kind of like this 12 minus the VBB, which is this power source right here, and the VBE, which is from base to emitter, which is this diode right here, 0.7. And then you get the IB, which is the current from this huge circuit here. And then from there, you can kind of tell what VCE will be by kind of the same VEE minus VICRC, which is what we did before, which is the VCE, right? Which is the VBB, I mean VCC instead of VEE. And then from here you get the impossible oversaturation, which is minus 101 volts, which is like that's 100% impossible. So it's basically 0 volts. And from here, what happens when the VBB is equals to 13 volts? As you can see, we have to make it higher this time. It's a little bit strange in that sense because when you talk about PNP, it's kind of differential. So if both sides are the same, it will never be, it will just kind of be cut off. So to make it like I mean, yeah, always just be cut off or oversaturation because it just does nothing, right? So you need one to be a little bit higher or a little bit lower than the 12 volts, right? So that's kind of like how you kind of predict it. So we put 13 in this case so that we can see it being cut off. So the thing about PNP as well is it starts off saturated. It starts off saturated. So at 0 volts, the motor or whatever you hooked up to it will be moving. And then you have to reach like 13 volts on your VBB to kind of stop it, right? As opposed to the NPN where you have to go up to kind of like 2 volts or whatever to start your motor. So that would be in this case. Yeah, so that's kind of the calculations. If you want me to get more into it, let me know. I'm just skimming it through it now, and then you can see the cutoff and stuff will be different. I'm gonna show it real quick. And then I'm gonna show you the library files, which I think we have time for. So this is, yeah. And then the same thing here, we just want to see the RC. Let me make another plot. And we paste it here. Yeah, and then you can see the cutoff and things like that, right? So you see the cutoff is around 10 volts because it's a little bit bigger, as I explained before. Any questions so far? No. If not, I'm just gonna keep moving. Okay. So now, we want to. Don't think I need to save this. I already have it saved. And then I don't know why I keep opening new ones, so I should probably just open it right there. Open projects. And let's do so this is the NPN for Darlington, which is the TIP122. I believe that is the NPN. for Darlington. Hopefully I am right. I'm not sure if I'm right, to be honest. Let me see. You can tell if it's MPN by the way that the circuit looks. All right, so yeah, so that looks like so this is a MPN. So instead of the 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 proper name, the TIP122, we have we use something in place of it, as you can see in your labs. 127 is PNP. Oh, thank you for attendance. Yeah, so this is the NPN. Yeah, and this is in place of the TIP122. We use this instead because we cannot. There is no library for that right now, right? So as you can see, if you type it in the parts list, I have all it highlighted right now. If you want to find TIP122, it's not possible. Oh, it is possible. It is in there. I did not know that. So you can use this actually. You can use this or another one, but in your lab it will say to use the this instead, which is it still works fine. I think there are some issues with this one, but I think if it works, it works, right? So you can do the Q2 and yeah, when you find this, it'll be more or less the same as the calculations will be more or less the same. I have the calculations here, but the only thing is the difference is did I put it? I did put the calculations in. So the calculation is more or less the same. The only difference would be the VBE. Instead of 0.7, it'd be 1.4. That is because there is 2 diodes. So keep that in mind when you're doing calculations. Yeah, let me just start it, and then you'll see that the cutoff point is also a little bit sooner than it's a little bit closer than to the 3.3 compared to the other NP, the other PNP. I mean the other MPN. So see here is 3 instead of the 1.5 that it was before. Now it's closer to the 3 volts when it's completely saturated or cut off, right? So this is, yeah. So as you can see here, it is cut off here and then saturation around 3 volts. And the same thing for the TIP127. Do you want to see TIP127 as well? You don't need to if you don't want to. I can show it quickly just so you guys can see what transistor I used instead of it. Let me just go to the open project. And the 127 we use, let me see. Here, we use 127, we use the 2N6052, as you can see here. And it's more or less the same. I think just the cutoff is not really, I think it's a little bit closer, if I remember correctly. Let me do this, add a new plot. Yeah, so it's closer to 9 volts as opposed to kind of like the 10 before. So it used to be like 10.5, I believe. So this one's 9 instead. So a little bit different. The calculation is a little bit different. Just the 1.4 added into 2. And you'll get the slides. So hopefully it'll help you guys out during your test and whatnot. Yeah. And the one more thing I want to talk to you guys about. We have 10 minutes. I want to show you guys how to add library files. So there is this thing that you guys will learn eventually, which is the PMOS and the NMOS. And they are, what are they called? And they are voltage driven transistors, right? NMOS and PMOS transistors. Yeah. So they're more voltage driven. So there's less calculations. It's kind of like when you see the voltage is 0, it's either cut off or saturated. So at 0 volts for the NMOS over here, let me show you. It is the threshold's around 3.87 volts. So if it's over that threshold, then it is saturated. If it's under that, it is cut off, kind of thing. And then the PMOS is kind of like PNP is the same. Yeah, this is MOSFET. Yeah, you're right. I apologize for not knowing the name, but you're right, Adam. It is MOSFET. Yeah, and then the PMOS is the same. So the thing about this is you need to add your own library files in there, because like if right now, if I wanted to do the IRF, let's say 840, it should not be here, right? It's not possible. It's not here, right? You don't see it here. So you need to add library files. So I believe, I think Rakesh will give you the library files, I hope. Or if he doesn't, we can ask him. I'll see if you can ask him to give you the library files. So there's the library files, which I have here. I have one for Darlington as well, but it's called breakout MOS. So this is to add the MOSFETs in your library. So how do you add that in? I have a whole slide about that, which is over here, right? So you find the OLB and .lib files somewhere. Hopefully, I think your prof will give them to you. I think Rakesh will give them to you. And then you kind of just put them into these places, right? Let me do another window and show you guys. So if you have this slide, which I'll give to you, so don't worry, you just copy this. So, and then you just put it in here. So if you download it on your C drive, it should be pretty simple. If not, you kind of have to find it based on the path. And so here you put in your .lib file. So let me find my .lib file. And then you just put it in here, right? And then you just replace it in the destination. Yeah. And then actually, I want to keep that file. Okay, cool. I want to copy this. So copy it instead, then you can keep the files. Yeah, and then now we want to go into this other place, which is this one. Copy it and you put it into here, and then you put your OLB file basically. The OLB file is kind of like the reading file that you have to put in. So, sorry, do you have a question or? Okay, cool. So yeah, you put the breakout file in here and cool. And then now you have it. And how do you add that into your library? Just gonna go here, right? And then you just add it the same way. You find it into this. Let me just breakout MOS, right? Open it. And then when you click on breakout MOS, you should have the IRF 905 here, which is what you need. So yeah, any questions? No, so far? Cool. All right, so I'm gonna show you the graph. It's more or less the same. This is just more voltage driven, so the current doesn't really matter. I don't know why I closed it. I should have just, I don't know. I do a lot of dumb things sometimes. So let me click open, go here. And then I have it already set up. Hello? You have a question? No? Okay. All right, we have 5 minutes. That's okay. All right. Cool. Why is it not showing anything? 1 second. IRF and schematic, page 1. Cool. And then we have DC. Yep. And the schematic. Oh, there you go. Okay. And then the same thing, you want to add a different plot so you have a nicer looking graph. Same thing for all of it. It's fine. And then yeah, and then you can see here, it's more exact. It's more like a straighter line as opposed to a curve. Sorry, is there a question? Someone say. Do you have a question? Hello? No? Can you please turn Adam's mic off? Okay, my bad. Yeah, I'll turn it off. I can see someone talking. There you go. I muted it. All right. So yeah, the 3 volts here and 4 volts. Yeah, I apologize, Adam. I couldn't really hear what you were saying. Yeah, so the cutoff, and then you see it's more like a straight line. So it cuts off more directly. The PMOS is more or less the same opposite way for the like the PNP. Yeah, I can show you that too. We have like 5 minutes, sure. Yeah. And any questions so far? Or you guys are good? Mahiti, or any one of you, Fatty? I guess if Fatty, you're here. Yeah, Fatty knows a lot about this stuff too. So, I don't know why I keep closing this. I can't. Yeah, this is just what I do all the time for some reason. 905, and then there is level shifting, which is like super complicated. I can go over that too if you guys want me to, but I think we're casual also. And yeah, and then you see the schematic for this. They are pretty simple. It's more simple for voltage driven, as you can see, because you don't really need a current limiting resistor compared to the PNP and the Darlington, like the BJTs and the Darlington. So you can see compared to this. See, there's a current limiting, there isn't. Yeah, oh, I didn't make a schematic for this, but let's see, the voltage is here. I didn't do probes for this, and then IC we want to just do here. Oh. Let's do it here. So you gotta put it like at the proper spot. And then you do the DC sweep. DC sweep voltage name V1, start value 1, and this is PMOS, so we should do it, let's say 13. Okay. Yep, and then you see, oh, there's no cutoff. Sometimes you have to play around the numbers a little bit. But let's see, 1 second. Let me see if this makes a difference. Yeah, so it does have a cutoff. But I think I put the voltage in wrong. So you see here, the cutoff is around 7 volts to 8 volts. And I believe I put this in wrong. Let me see if I can fix that. Where do I put the probes? If I remember correctly, it is here. Oh, I know. I think I gotta put one here and here. Let's see if this works. Doesn't seem to be. That's okay. But you kind of get the gist of it, I hope. If you guys have any questions, let me know. No question? Good. And if you want me to go over level shifting, I can too. If not, that's fine. No questions? Cool. Okay. I'll stop my recording here. Actually, let me go over level shifting real quick. So level shifting is basically just using what is it here? Using two transistors, using a FET and using a BJT or Darlington to drive it, right? And then the calculations are here. So if you need to go to more detail, I think talk to Rakesh, or you can ask me now. I'm gonna stop the recording. Here. Stop recording.